Welcome. In today's discussion, we are diving into a foundational process for any engineering or manufacturing discipline, the creation of an accurate bill of materials or BOM directly from your CAD designs. So what is a BOM? At its core, it's a comprehensive list of all the raw materials, sub-assemblies, intermediate assemblies, subcomponents, parts, and the quantities of each needed to manufacture a final product. It is the recipe, the blueprint, and the shopping list all in one. Without an accurate BOM, you risk production delays, cost overruns, and incorrect assemblies. The key to automating this process lies in attributes. Think of attributes as intelligent metadata or data about data that we embed directly into our reusable CAD components known as blocks. This isn't just geometric information, it's the part number, the material specification, the supplier, the cost, all the rich information that traditional BOMs require. To manage this effectively, we'll explore a suite of powerful tools within modern CAD software. We'll look at blocks for creating standardized reusable components. We'll discuss XREFs or external references for managing large collaborative projects. And we'll see how the Design Center helps us maintain consistency by creating centralized component libraries. Finally, we'll walk through how we can leverage commands like data extraction to automatically pull all this embedded attribute information into a structured, accurate, and exportable BOM, transforming a tedious manual task into an efficient, reliable workflow. Let's build from the ground up by looking at the absolute foundation of an intelligent BOM system: blocks and their attributes. In the world of CAD, a block is a collection of objects, lines, arcs, circles that are combined to form a single, named object. The true power of a block is that it's a reusable component. Instead of drawing a standard M6 bolt 100 times, you draw it once, define it as a block, and then insert it wherever needed. This ensures consistency and saves an enormous amount of time. But a block is just geometry until we add intelligence. That's where attributes come in. Using a command like attdef, which stands for attribute definition, we can attach non-graphical text information to a block. When defining an attribute, we specify a unique tag, which is like a variable name, such as partno. We create a prompt like enter the part number, which guides the user during block insertion. And we can assign a default value. We create attributes for every piece of data we need in our BOM, a unique part number for identification, a detailed description for clarity, the specified material for manufacturing, the supplier, and even the unit cost for budgeting. Every time we insert that block, we are not just placing a drawing element, we are placing a data-rich component that carries its own essential information, forming the very bedrock of the data we later extract for our BOM. As projects grow in complexity, a single drawing file can become unwieldy. This is where we leverage a powerful feature for modular design, XREFs or external references. An XREF is essentially a link to another drawing file that you can display as part of your current drawing without actually inserting its geometry. Imagine designing a complex machine like a car. One team can work on the engine and its own drawing file, another team on the chassis, and a third on the interior. The lead designer can then create a master assembly drawing and use XREFs to bring in the engine, chassis, and interior files. This approach keeps file sizes manageable, allows for concurrent work, and ensures that when a sub-assembly is updated, the change is automatically reflected in the master drawing. However, this poses a critical question for our BOM. How do we capture the attribute data from these externally referenced files? If we only analyze the master drawing, we'll miss all the parts from the sub-assemblies. The solution requires proper management. During the data extraction process, we must explicitly choose to include data from XREFs. Alternatively, for a final archival drawing, we might bind the XREFs, which permanently merges them into the master file. Failing to account for XREFs is one of the most common ways to generate an incomplete and inaccurate BOM, so understanding how to handle them is essential for any complex project. Consistency is the cornerstone of reliable automation. In a team environment, if 10 different designers create their own version of a standard bolt, you'll end up with 10 different block names and potentially inconsistent attribute data, making a unified BOM impossible. This is the problem that the Design Center or a similar content palette tool solves. Think of the Design Center as your company's official, centralized library for all approved CAD assets. Here you store your standardized blocks, each one meticulously created with the correct geometry on the right layers and most importantly, with a full set of predefined, accurate attributes. Whenever a designer needs a component, they don't create it from scratch. They simply open the Design Center, navigate to the correct library, and drag and drop the approved block into their drawing. This simple action has profound implications for data integrity. It guarantees that every single time a specific part is used across every project in the entire organization, it carries the exact same part number, description, material, and cost information. This enforcement of standards eliminates a huge source of potential error and is absolutely critical for ensuring the data you extract for your BOM is clean, consistent, and trustworthy. It transforms the design process from an individual craft into a systematic, scalable engineering workflow.
We have now defined our data-rich blocks, managed our modular assemblies with XREFs, and standardized everything with the Design Center. The final step is to harvest this information. This is accomplished using a powerful wizard-driven tool, often called data extraction. This tool automates the entire process of scanning your drawings and pulling out the attribute information you need. Let's walk through the key steps. The process begins with selecting your data source. You can choose the current drawing or you can select multiple drawings at once, which is incredibly useful for project-wide reports. Crucially, this is where you tell the software whether to include the data from any attached XREFs to ensure you capture everything. The next step is filtering. A typical drawing contains thousands of objects, lines, dimensions, text notes, but we are only interested in our blocks. The wizard allows us to filter the selection so we can tell it to ignore everything except blocks. We can even refine this further by selecting only blocks on specific layers or with certain names. Once we've isolated the components we care about, we move to the final selection step, choosing which attributes to extract. We'll be presented with a list of all available attributes from the selected blocks, like part number, desk, material, cost, and we simply check the boxes for the data columns we want in our final BOM. This structured step-by-step process gives us complete control, ensuring the final output is precise and tailored to our exact needs. After we've told the data extraction wizard which blocks and attributes we are interested in, one of the most powerful functions occurs: automated summarization. The tool intelligently scans all the selected source files, identifies every instance of each unique block, and counts it. If you have inserted your M6 bolt block 72 times throughout your assembly, the tool will automatically calculate a quantity of 72. This step alone saves countless hours of tedious, error-prone manual counting and is a cornerstone of this automated workflow. You can format the output right within the wizard, sorting columns and setting titles. Once the data is refined, counted, and summarized, you have options for the final output. The first option is to insert the complete bill of materials as a table directly onto your CAD drawing. This is great for keeping the parts list and the drawing together as a single deliverable. The second and often more powerful option is to export the data to an external file. The most common choice is a Microsoft Excel spreadsheet or a CSV file. Exporting to Excel unlocks a world of possibilities. You can perform further calculations such as totaling costs, you can sort and filter the data in more advanced ways, and most importantly, you can use this file as a bridge to other business systems, feeding this precise manufacturing data directly into your procurement and planning software. Once you have mastered the fundamentals, you can explore several advanced techniques to further enhance your BOM workflows. First, consider dynamic blocks. These are super blocks that can be configured with different states or parameters. For example, you could have a single bolt block that through a simple drop-down menu can be changed to different lengths or diameters with all its associated attributes updating automatically. This dramatically simplifies your block library. Next, we have field-linked attributes. A field is a piece of text that can automatically update when a data source changes. You could link an attribute to an object's property so that if you stretch a part to change its length, the length attribute in the block updates automatically, ensuring your BOM is always in sync with the geometry. For the ultimate level of customization, you can use scripting languages like Lisp. With Lisp, you can write custom programs to automate any repetitive task, create unique data extraction routines, or perform complex validation checks on your blocks and attributes. Finally, the ultimate goal for many organizations is full enterprise resource planning or ERP integration. This involves creating a seamless pipeline where the BOM data exported from CAD is automatically fed into the company's central ERP system. This direct link automates everything downstream: purchasing orders for materials, inventory management, and production scheduling, creating a truly integrated digital thread from design to manufacturing. To conclude, let's crystallize the best practices that are essential for maintaining a robust and reliable automated BOM system. None of this works without unwavering consistency. You must establish and, more importantly, enforce a strict and logical naming convention for everything: your block names, your attribute tags, and your layer names. This discipline is the language that allows the automation to work. Second, a simple but incredibly effective practice is to place all your data-rich blocks on a dedicated layer. For example, a layer named BOM Components. When it comes time to extract data, you can simply tell the system to look only at that one layer, making your filtering process instant and foolproof. Third, this is not a set-it-and-forget-it system. You must implement processes for validation and conduct regular audits. Periodically review your design center libraries to ensure all data is current. Check for unapproved blocks in drawings and validate that attributes are being filled in correctly. This proactive maintenance prevents small errors from becoming major production problems. By adhering to these principles: standardization, organization, and validation, you will achieve the three primary goals of this entire endeavor. You will create a workflow that is incredibly accurate, minimizing costly manufacturing errors. It will be vastly more efficient, saving engineers hundreds of hours of manual data entry, and it will be scalable, capable of handling projects of any size and complexity, providing a competitive advantage for any modern engineering team.